Hey, hello, calculus students. I apologize for the lesson one technical glitches. Zoom didn't work for about 2 hours for me, and then all of a sudden it just started to work. So anyway, we'll try again. Lesson two is the mean value theorem, and I can never pronounce this one correctly. Monetosity, I think it is. But you're looking at the slope of the line. You want to know, where is it increasing, where is it decreasing? So we will identify relative maxima and minima on a curve. Now, if you did happen to watch yesterday's video, I went over an example of how to do this already. So I'm just going to reinforce that. The mean value theorem, let f be continuous on the closed interval a, b, that's what the brackets are, and differentiable on the open interval from a to b, that's what the parentheses are. Then there exists at least one point C in AB such that f prime of C is equal to f of B minus f of A over B minus A. Calculus theorems are very wordy. So what about in English? Between any 2 points on a differentiable function, there's at least one place where the secant line between the points and the tangent line are parallel. So you can connect the two endpoints for a secant line, and somewhere between those endpoints, there has to be at least one location that has a parallel slope. Now, the figure that's in front of you actually is 2. So they drew one down here at C, right here, parallel to my secant line, but there would actually be another one over here. So we could call this one C1 and this one C2. You don't want to get it confused with the intermediate value theorem. So the intermediate value theorem says you have to have a continuous function, and you've got, if you've got two y values and one in between, then the x value would also be in between the endpoints. The mean value theorem is specific to the slope. And in fact, what I tell students is it's slope equals slope. The left-hand side is slope from calculus. The right-hand side is slope from Algebra 1. And this is really just y2 minus y1 over x2 minus x1. Same thing. We just don't use x's and y's in calculus. We use a's and f's. So find the value for which the mean value theorem applies for f of x equals the square root of x from a equals 1 to b equals 9. So we're going to jump right in. Here's my mean value theorem. F prime of c is equal to f of b minus f of a over b minus a. So f prime of c, c is what we're looking for, so that stays there, is f of 9 minus f of 1 over 9 minus 1. Now, to get those f values, you're really just substituting it into the original function. So this is square root of 9 minus the square root of 1 over 9 minus 1. And f prime of c, actually we should fill that in. What's the derivative? Let's come over here. F prime of x. This is really x to the 1/2, so this is a power rule 1/2 x to the negative 1/2. So I'm going to actually make this 1 over 2. I'm going to take that x to the negative 1/2 and move it to the denominator. 1 over 2 root x. Like that. Okay. Now, the right-hand side, we need to clean this up a little bit. So I have 1 over 2 root x. This is 3 minus 1 over 9 minus 1 is 8. So the numerator is, that's a 1. 2 over 8. I may as well reduce that to 1/4. Now, how do we solve this? Well, if I have a fraction equals a fraction, this is a proportion. I'm going to cross multiply. I'm going to say that 4 is equal to 2 root x. I'm going to divide both sides by 2. So 2 is equal to the square root of x. Square both sides, and so x is equal to 4. Is x equals 4? That's actually my c, I guess. Is that between 1 and 9? Well, yeah, it is. And I know, yeah, let's do this. We have the technology, we may as well use it, right? So square root of x, y equals, where's my square root? Square root of x. Okay, ta-da. And we are looking at the square root of x between 0, 0, the origin, actually 1 and 9. So we're looking from x equals 1, 2. How do I make another one? There we go. X equals 9. Now I'm just using those because I can't draw on the picture as to exactly where those are. Now we had said that at 4, there exists a parallel tangent line. I'm not asking you to find the slope of the line, even though we did as the 1/4. I'm not asking you to find the equation of the tangent line, even though you could. I'm just saying at 4, there exists a slope that is parallel to the slope that would connect the two endpoints. That's all I'm saying. All right, let's go back here to notability. All right, here we go. Assume f of x is differentiable and f prime of x equals 0 for all of x on a to b. And f of x is constant in the interval. We're looking at increasing and decreasing nature of the functions. If f prime of x is greater than 0, then f of x is increasing. If f prime of x is less than 0, then f of x is decreasing. It's important that you use that terminology correctly. F prime of x is not increasing, but the original function f of x is increasing. F prime of x is not decreasing. F of x, the original function, is decreasing. And another thing that you should know is this is just a fancy way to say positive. And again, fancy way to say negative. Example 2, find the intervals of f of x equals x squared minus 2x minus 3 that increase or decrease. Now, this is a very simple, straightforward example. You won't see one this straightforward on any examples on any AP problems, but it's a very good place to start. You know that x squared is a parabola. You know that a positive x squared opens up. So I don't know exactly what it looks like, but I know that it opens up like that. We want to figure out where it increases or decreases. Increase or decrease comes from the first derivative. So let's calculate the first derivative. 2x minus 2. Yesterday, we were finding critical points. So let's set this equal to 0 and solve for a critical point. I'm going to factor out a 2. Lots of factoring in this unit. X equals 1 is my critical point. Great. That means I have a horizontal tangent line. It's a maximum or a minimum. Well, if it's a horizontal tangent line and I know the parabola opens up, this is a minimum. But I want to show you how that works. So x equals 1. So you're going to make a number line. And in years past, students have told me that they did this in pre-calculus to figure out where the function was above or below the x-axis. We're going to do the same thing here. You are going to look for not above or below, but increasing and decreasing. So we want to put this into the first derivative. So what's a number that's a little smaller than 1? You could use 0.9. I know we did that in the limit unit, but integers are much easier. I'm going to go with 0. 0 is super easy. So if I think 0 in my brain, I put it in the first derivative. So 2 times 0 is 0. 0 minus 2 is negative 2. I just want the sign. I just want to know that it's negative. I don't care about the value because I use 0 and maybe the person next to me used negative 1. Then to the right-hand side of 1, we need a value that's bigger than 1. Again, you could use 1.1, but we usually just use integers for these if we can. So we go to 2. So if I put 2 into here, 2 times 2 is 4. 4 minus 2 is 2. It's positive. You can also use the factored version. That's kind of nice too. So where it's negative, we say f of x is decreasing from negative infinity to 1. And we say f of x is increasing from 1 to infinity. Now, a couple things to note about this. We all use the table to organize our work, but it's never, ever, ever considered a justification in an AP free response question. You would have to say that f prime of x is less than 0. Therefore, f of x is decreasing. In fact, let's do that. F prime of x is less than 0. I'm going to go with so because it fits. So f of x is decreasing from -1 to 0. F prime of x is greater than 0 on the interval from 1 to infinity. So f of x is increasing. So the piece in blue you could use as AP justification. The number line you can't, but it's a really good way to organize your work. All right, works for my picture. Excuse me. So the left-hand side is negative slope, the right-hand side is positive slope. Okay. First derivative test, let's take it a step further. If f of x is differentiable and c is a critical point, f prime of c changes from positive to negative, then f of c is a maximum. If f prime of c changes from negative to positive, then f of c is a minimum. And you know what? Instead of c's here, these should probably be x's. F of x, because c is a point and f of x is the curve itself. So I want to analyze the critical points of f of x equals x cubed minus 27x minus 20. So critical point. If I see critical point, that means first derivative. So the first derivative is 3x squared minus 27. Now, critical point, we set this equal to 0. X squared minus 9. I told you yesterday you'd be tired of critical point. And then I'm going to factor x plus 3, x minus 3. So what are my solutions? My solutions are -3 and 3. These are critical points. So I want to figure out, are they a maximum or a minimum? So I'm going to put them on that number line we just did in the last example. And we are going to substitute not into the original, but into the first derivative. So let's go with another color. So a number less than -3, I'm thinking -4. Now, instead of messing with the square and subtracting, I'm going to put it down here. It just works better for me, the factored version. So a -4 in the first piece makes this negative, and the second piece makes that negative. So negative times a negative is a positive. Now, between -3 and 3, you've got lots of choices, but 0 is a nice one. If I put 0 in this version, 0 minus 27 is a negative. Now, a number larger than 3, say +4. Down here, I like the factored one again. That's a positive. This is a positive. A positive times a positive is a positive. Now, a couple of things to note before we go further. Do the signs have to alternate? The answer is no. Do they alternate often? Yes. They don't have to alternate. Think back to pre-calculus. When do they not have to alternate? Double roots is an example where they don't have to alternate. Eventually we'll get into vertical asymptotes. They don't have to alternate. So just be careful. Don't be like, oh, the first one's positive. I'm just gonna, keep going on my way and alternate. Not the case. I want you to check every single interval. I know it's a little extra work, but you can do it. So we are increasing from -infinity to -3 and from 3 to infinity. We are decreasing from -3 to 3. Now, the question was about the critical points. So x equals -3. I go from positive to negative. I go from uphill to downhill. So if you switch from going uphill to downhill, at the top you have a maximum. At x equals 3, I go from downhill to uphill. So I switch from going downhill to uphill. That's a minimum. By the way, those are local maxes and mins. We talked about absolute yesterday, so we're not talking about y values. I don't know which is higher, which is lower. We don't have endpoints. I'm just talking about a little mountain and a little valley. Good. This would be a good one for you to try on your own. Analyze the critical points of 1/3 x cubed minus x squared plus x. And I actually think this is our last example today. It is. So if you want to pause it and come back and try, might not be a bad idea. Let's switch colors here. Dark blue was kind of cool. So f prime of x is 1/3 3x squared minus 2x plus 1. Set this equal to 0 for a critical point. My 1/3 and my 3 cancel out. So x squared minus 2x plus 1. Factoring is your friends. X minus 1, x minus 1. So x is equal to 1. Now, you might have a little red flag going off. Hey, you have the same answer twice. This is that double root situation I was talking about a moment ago. So you want to find your number line. Here's the 1. We're going into the first derivative. I wrote x. This is 1. A number less than 1 is 0. So if I put 0 in here, this is a negative times a negative is a positive. If I choose a number larger than 1, say 2, this is a positive times a positive. So we have increasing, increasing. We'll check this out momentarily. So we are increasing from, now I always have students break it apart, negative infinity to 1 and 1 to infinity. Because at 1, you're not actually increasing, you are horizontal. Include the break for me. Depending on the resources that you're looking at, the textbook, the website, they might say that it's increasing from negative infinity to infinity. They might say it's increasing everywhere, but you have to be careful of that one place where it's not. What does this one look like? 1/3 x cubed minus x squared plus x. Let's get rid of these. Y equals 1/3 x cubed plus x squared plus x. Okay. You can kind of see it here. Oh, wait, I think I missed a sign. Yep, a minus 2x plus 1 minus x squared. That'll make a difference. There we go. There's my shift. So this is a cubic function. And those other terms just kind of shifted a little bit. So if I zoom in here and look at 1, yeah, I can see that it goes horizontal. That's a critical point. That critical point is neither a max nor a min, but it does have a horizontal slope there. So if I come back over here, I should say that x equals 0. Nope, excuse me, x equals 1. Oh, my pen is really slow. X equals 1. Neither max nor min. There it comes. All right, so neither max nor min. You have to have a sign change by that first derivative test, and we don't. It stays positive, positive. So again, I mentioned yesterday, this unit just builds. Everything that we just did with the first derivative, we're going to do with the second derivative in, I think, 2 lessons. So make sure that you're feeling really good about these. And if you're not, reach out for help. You know, we're here to help. So good luck.